Hello everyone. Thanks for watching this presentation. I am Tanvir Ahmed Khan, a fourth year PhD student from University of Michigan. Today I will present our work I Spy. In this work, we propose two novel prefetching techniques to avoid frequent instruction cache misses. Instruction cache or I-cache misses is a major problem for data center applications. We characterize the implications of this problem for 9 data center applications. These data center applications are widely deployed in many companies, including Facebook, Twitter, and Netflix. For these applications, we measure percentage of CPU cycles lost due to I-cache misses. We show these lost cycles in y-axis where lower is better. Unfortunately, these applications lose 20 to 70% of all CPU cycles due to I-cache misses. That is because data center applications typically have large instruction footprints that cannot fit into modern CPU I-caches. To tackle this problem, a rich body of prior works have been proposed in the literature. Unfortunately, these prior works have several key limitations. Such limitations include requirement of significant hardware modifications, impractical on-chip metadata storage, and partial performance gain due to inaccurate approximations. To understand these limitations, we look closer into the state-of-the-art ASMDB. ASMDB is a profile-guided software instruction prefetching technique from Google. ASMDB analyzes the execution profile of data center applications to identify I-cache misses. This work observes that I-cache misses happen when an instruction changes the program control flow and the program executes the next instruction from a different cache line. Based on profile, ASMDB finds a predecessor that can predict the I-cache miss with highest accuracy. By predecessor, I mean instructions that are executed before the miss. ASMDB then inserts a code prefetch instruction on that predecessor in order to avoid the miss. We evaluate ASMDB's speedup for 9 data center applications and compare this speedup against the speedup of a simulated ideal cache. This ideal cache has infinite capacity and therefore does not suffer any misses. We find that there is a significant performance gap between speedup provided by ASMDB and the speedup of an ideal cache. In this work, we first study and understand the reasons behind this performance gap. Next, we propose two new techniques, conditional prefetching and prefetch coalescing, to close this performance gap. Both of these techniques can be implemented with minor hardware modifications. Specifically, they require only 96 bits of extra on-chip storage. Finally, our proposal I Spy provides on average 90% of ideal cache speed up. Let us first understand the challenges of designing a prefetcher that can provide near ideal cache speedup. One of the fundamental challenges of this near ideal prefetcher is the trade-off between cache miss coverage and prefetch accuracy. To illustrate this trade-off, we plot cache miss coverage of the prefetcher in the x-axis. Miss coverage denotes percentage of all original cache misses that the prefetcher can avoid. Therefore, higher is better. In the left y-axis, we show percentage of ideal cache speedup that the prefetcher can provide. Again, higher is better. In the right y-axis, we show the prefetch accuracy. Prefetch accuracy denotes percentage of prefetched cache lines that are actually used, and therefore higher is better. As shown, prefetch accuracy drops significantly with an increase in miss coverage. This means we can cover most misses only if we sacrifice the accuracy of the prefetch. Consequently, only 65% of ideal cache speedup is achieved even with the highest miss coverage. To overcome this challenge, we propose conditional prefetching. Going back to the earlier example, the accuracy of prefetch falls since the prefetched cache line is not used always. To improve this accuracy, we look even further in the execution history. Due to program nature, same or similar conditions are used multiple times throughout the lifetime of a program. In this example, execution of B also depends on the same condition. Using this program characteristic, we can add a condition for the prefetch instruction so that the prefetch will be enabled only if B was executed recently. We identify B as the context for the prefetch and call this technique context-driven conditional prefetching. This technique can be implemented with only 96 bits of extra on-chip metadata storage. We encourage reading our paper for more details. Another key problem of profile-guided software prefetching is code footprint increase due to added prefetch instructions. We show this code bloat impact in the y-axis where lower is better. As shown, code bloat increases with higher miss coverages. Specifically for the highest miss coverage, we see around 14% code bloat, which introduces new iCache misses as a side effect. We propose prefetch coalescing to limit this code bloat. For many applications, we observe many prefetch instructions that bring in nearby cache lines. We can consider one of those prefetch as base and represent the remaining ones with the small bit mask. This bit mask then can be used as another prefetch parameter to coalesce multiple prefetch instructions into a single one. This way, the original 21 bytes of prefetch instructions can be replaced by only 8 bytes of prefetch instruction. Moreover, multiple conditional prefetches can be coalesced as well if they depend on the same condition. We evaluate the effectiveness of our proposed techniques by measuring the reduction in iCache miss per kilo instructions or MPKI. We show the MPKI reduction percentage in the y-axis where higher is better. As shown, our proposed approach iSpy reduces more misses than the state-of-the-art ASMDB. Specifically, iSpy reduces on average 96% of all iCache misses. In conclusion, we propose iSpy, a combination of context-driven conditional prefetching and prefetch coalescing. iSpy reduces on average 96% of all iCache misses for 9 dataset applications. We show that iSpy can be implemented with minor hardware modifications. On average, iSpy provides 90% of ideal cache performance for these 9 dataset applications. Thanks once again for watching this presentation.